So I'm going to talk about how to build better deep learning-based models for image reconstruction. So I'm going to talk about some work that is joint work with a number of collaborators. So there's going to be some work that has been done by Mohammed, and Mohammed is a PhD student at Rice University. Then there's going to be some work that has been done with Toby de Kloek. He's a PhD student at the Technical University of Munich. And then Akshay is a collaborator in magnetic resonance imaging, and he helps make sure that we are doing the right things regarding magnetic resonance imaging. All right, so I'm going to focus on accelerated magnetic resonance imaging as an inverse problem, but most of the things I'm going to talk about, they apply to other inverse problems, for example, in microscopy or denoising, things like that. So the problem is as follows. We have an image, like say a knee, and we collect 4 times undersampled data in this case. So the lines are the frequencies that we collect, and the black lines, that is data that we don't see, frequencies that we don't see. So now the goal is to estimate an original or the original image from this undersampled data. So there are a number of methods for MRI reconstruction. So for example, L1 minimization, total variation minimization, things like that. So there are a lot of classical optimization-based algorithms that work really well. But it turns out that deep neural networks trained end-to-end perform best. So deep neural networks trained end-to-end means the networks are trained on examples that consists of measurements and output images, right? And the output images are typically obtained by reconstructing from the full case-based data. And there are a number of ways actually how to use neural networks in this context. So for example, we heard about generative approaches, and there are also ways how to use neural networks without any training. So Ben talked about this yesterday, for example. Marty talked about how to use neural networks in this way. But it turns out this approach to using training neural networks end-to-end, that really performs best, both in terms of computation performance. It's extremely fast. We only have to do a forward pass through the network, and also gives us best image quality. So there are 2 components to the performance of these neural networks, and those 2 components very broadly are the models and algorithms. So models means the particular neural network that we use, and algorithms means everything around it. So for example, how we train these neural networks and how we use them. And then there's, of course, the data that we train the networks on. So now let's look at some other field in machine learning. Let's look at natural language processing. So what happened in natural language processing was that, or what still happens is that if you increase the models in natural language processing, you get predictably better performance. So if you increase the models and the data at the same time. So you see this here. So let's look at the plot in the middle. So what we see here is the performance of language models as a function of the data size. And it's a log-log plot. So what we see is that as we increase the data set size, we get predictably better performance, right? And there's no, there's no slowing of these scaling laws. So this is really nice because it tells us for language models, we can simply collect more data. It's obviously going to be very expensive because those are already billions of tokens, right? But if we collect more data and if we increase our models at the same time, so that's very important. So we cannot take the same model. We also have to increase our model. Then we get better performance. Yeah.
Could you please explain the left-hand plot at least? Like, what are these blue lines and so on?
So what these things mean, so I really want to focus on the middle plot, the data set size. So the way how to interpret that plot is each point corresponds to a model trained on the data set size that is given there.
But using the same algorithm, the same network?
Not exactly, not the same network. Well, kind of the same network, but the parameters are chosen differently. For example, if you have a very small data set size, then what you have to do is you typically have a smaller network that performs best. So in a way, for each point, the hyperparameters for the model are chosen as well as people can. Yeah.
Just curiosity, what is a data point in a language model? Is it a word or a book?
Yeah, let's actually, let's talk about this in the context maybe of classification. So here's like tokens, right? Means like, so it could, for example, be sentences, right? And then you have a sentence and you leave something out, right? And you use this as training, and you can view this as a token. Yeah. Okay, here's another example. Maybe here it's really much clearer what this means. So same experiment, but this time it's for image classification. So what we see here is we see the dataset size in terms of millions, and then we see the ImageNet error rate. And also what you can see here, very similar thing, that if you increase the dataset size, and if you choose a larger model, and of course you have to choose hyperparameters, right, and it's non-trivial, then you get predictably a better performance. And also these scaling laws are also not really slowing, so presumably as we increase the dataset size further, we would get better performance. Yeah.
So why do you say predictively? In which way is it predictive? I mean, these are numerical experiments.
Those are numerical experiments, right? So we don't know for sure, obviously, what's going to happen, right? But the scaling laws don't slow, so this suggests that if we increase the data further, that it would continue on this scale.
But it's a hypothesis.
It's a hypothesis, but it has been validated, at least, for example, what people have been done is they made these scaling laws, and then they increased the data set size, and then they found it continues, right? But there's only so and so much that you can do, right? At some point, it's hard to collect more data. So of course, it's also not going to continue forever, and we're going to talk about this later.
Yeah. So it's a little bit like Moore's law or something, where you say like, so far people have made.
It's a little bit like Moore's law. Of course, it's not like, and of course it cannot go like this indefinitely and so on. So that's very clear. Good point. Okay, but kind of seeing that, now let's go back to image reconstruction problems. So now if we look at image reconstruction problems, it turns out that there the data set size is actually really small. So here are a few examples. Those are all like very, well-received papers, very highly cited papers. So for example, there's a paper on image super resolution. It gives excellent performance to that date. It's trained on 90 images. Then there's denoising with CNNs, trained on 400 images. Then there's a fast MRI data set for MRI. It's the data set is 35,000 images large or slices large. And then there's the Swin transformer for denoising. That's like the state-of-the-art model for denoising right now. It gives you best performance for Gaussian denoising. That is trained on 10,000 images. So what we see here is that the data set sizes in image reconstruction problems are relatively small relative to prediction tasks. Prediction tasks is things like natural language processing, classification, and so on. And so when we saw this, we were wondering, well, can scaling the data set size improve the performance for image reconstruction problems, right? Because if things behave as in natural language processing or in image classification, then what we can do is we can just collect more data, and then we get predictably, not predictably, then we get, or we expect to get better models, right? Okay, so now let's see what kind of behavior we would expect. So let's look at a very, very simple model. So let's say we have a signal X that is drawn from a d-dimensional subspace. So in reality, we have an image X, and that's a natural image. It's hard maybe to model a natural image, but kind of a subspace is just some low-dimensional model, right? So X comes from some d-dimensional subspace. Then we take a measurement, a noisy measurement. So Y is equal to X plus Z, where Z is Gaussian noise. And then we consider a linear estimator, because for this problem, a linear estimator is actually optimal. So we consider a linear estimator that is trained on n examples through empirical risk minimization, because that's how the neural networks are trained. They are trained on empirical risk minimization. So what is empirical risk minimization? There's this risk, right? And we just sum over the loss over our, so W times Y, right? That's our prediction, so our reconstruction. And X is the image that we want to obtain. And so we train over, we optimize over W. So now we can show that if we regularize, so we do have to regularize in this case, but the optimal early stopped estimator obeys the following equation. So the mean square error is smaller or equal to the mean square error corresponding to the optimal estimator plus, and then we have some term divided by n. So now what this suggests is the following. So it suggests the following expected performance behavior. So here's the error in log scale, and then if we only train on extremely few training examples, like let's say 1 or 2, then we expect things to not work well, right? So then we are really like over here, sorry. Then we are over here. Then we are over here, right? But after that, we expect that there is some power law region, and power law region means a region where the error decays as n to the power of minus alpha, and for this toy problem, alpha is 1. And then, of course, it doesn't continue like this forever, right? Then there's going to come some region, when we have enough training examples, there's going to come this region where the error doesn't really improve because we achieve this irreducible error. And the irreducible error for denoising would be determined by the noise level, right? So once we are kind of in the noise floor, we don't expect further improvements by more training data, right? And we expect the same thing to happen for MRI and for other image reconstruction problems.
Can I ask a question? I may have misheard you. This is just a simple toy problem.
That's a simple.
Considering a linear filter, just as a demonstration.
Yes, just to see, just to see what we would expect. But we would kind of expect something very similar, like for most problems, right? Because imagine we have some complicated manifold, we have some model, there's going to come some point where we don't expect any further improvement, like when it goes to optimal. Yeah.
Okay, thank you.
Okay, so then the question really is, like, are we right now in this power law region, or are we already in this irreducible error region? Because if we are still in this power law region, for example, it looks like for natural language processing and for image classification, it really looks like we are still in this power law region, meaning that if we increase the data set size, we expect to get better performance. But for image reconstruction, it's kind of unclear whether we are in this power law region or whether the scaling law is already slowing and more data doesn't really help. Okay, so now let's look at some experiments in order to get some intuition on where we are. So here we have the following experiment. So here we do U-net-based denoising. So U-net-based denoising means we take a U-net. So U-net is an extremely good CNN-based denoiser. And we do the following experiment. So we take a certain training set size. So for example, here we take 100 images, right? And then for 100 images, we train different units, so units of different sizes, essentially, with different hyperparameters. So here you can see the sizes of the units. And then whatever unit performs best, right? So in this case, this one performs best. This is going to be this particular point. So we make sure that as we are scaling the data set size, we are also scaling the model size. And that's important, as you see, because there's kind of like a point of number of network parameters where we get the best performance for a given training set size. Okay, and so what we see is, like, so when we are in, like here, like in this region here, perhaps, right, like we have a relatively steep scaling law. I mean, it's not super steep, but once we are above, like, let's say 10,000 training examples, then this power law gets, or the rate of improvement that we get gets extremely slow. Because as you can see here, this axis here, those are dBs, right? So this is like an extremely small difference. So, like, of course, we don't know how these scaling laws continue, right? But we expect that they don't get steeper again. And if they continue at that rate, that suggests that at least for U-net-based denoising, increasing the data set size further has like very marginal benefits. Okay, so now let's look at another problem. So exactly same experiment, but now for accelerated MRI. Again, a U-net, accelerated MRI, and same experiment, right? What you can see here is behaves very similar. So once we have around, I don't know, a few thousand training examples, between 1,000 and 10,000, the rate of performance increase slows significantly. And so if we could increase this data set significantly further, we wouldn't expect much performance increase. And this time performance is measured in 1 minus SSIM, so not in PSNR. Yeah.
So why are you changing the figure of merit over the different experiments? Is there any non-robustness, or like, I mean, does it just look better in this score, or?
No, it's just for this data set, people measure performance in SSIM, and for denoising, people measure performance typically in PSNR. So for example, there's this fast MI competition, and their performance is measured in SSIM, and we just wanted to conform kind of with the standards of the community. Yeah. So it doesn't really look different in the different scores. It's also a very related score, actually. Okay, so now maybe you're aware of what has been happening in the machine learning community. So what has been happening in the past 3-4 years is people have realized that transformers are very powerful in the sense that transformers are an architecture that scale very well. So for example, if you take a CNN and you make it larger, at some point the performance doesn't increase that much anymore. But transformer-based architectures often have this property that if you make them very large and you train them on a lot of data, then they perform really well, right? And we saw this also yesterday in Marty's talk. They also achieved state-of-the-art performance on MRI, like using transformers, right? So then the question is, well, how does it look like for transformer-based architectures? So it looks very similar for transformer-based architectures. So this is the Swin transformer. And here, again, the denoising experiment. So what you see here is the curve looks very similar as the CNN-based denoiser here. It just performs overall a little bit better, right? So on each scale, it just performs better. And so here, the same story, like as we increase the data set size to like to around 100,000, like at some point we get very marginal performance increases. And those points here actually, this really gives you state-of-the-art performance overall. So we found, like we looked at 4 different data sets, and this model here really gives you state-of-the-art performance on 4 denoising data sets. So it's an extremely good model. So it tells you that, you know, like scaling things does improve the models, but you get really marginal improvements. So we are already in this regime where we get extremely marginal performance improvements. Okay, so the conclusion so far is that we get very marginal in-distribution gains expected from scaling data. So I'm going to explain what I mean with in-distribution gains in a second. I would also argue that we get very marginal in-distribution gains from model improvements on things like fast MRI. So for example, like Marty was also showing yesterday, the fast MRI, the models on fast MRI, and you could see that all the scores are extremely close to each other, right? So in the past few years, it has become very difficult to improve the models to get better performance. So there's also relatively marginal in-distribution gains from model improvements on this data set. So what does in-distribution gains mean? So here I want to explain again what the experiment is. It's going to be important. It might seem trivial. So the experiment is like this, right? In fast MRI, people were collecting measurements of, like, let's say, knees in one hospital on one scanner, right? And the scanner was the same, more or less. The patient population was the same, and so on. And then they were splitting this data into a training set and a test set. So of course, the training set and the test set, they are disjoint, right? But they really come from the same, what we call distribution. So now if we train on the training set and then measure performance on this test set, and they come from the same data source, that is in-distribution performance. And so what I want to argue in the following is, and this might not reflect performance in practice, right? Because what you actually do is, Siemens, for example, they have a deep learning model. It's trained on some data. You can use this model. You pay for it, obviously. But then you are applying it to your data in your hospital. It might be a different patient population, slightly different settings of the scanner, things like that, right? So that's how you typically use the models. So this in-distribution evaluation might not reflect performance in practice. Okay, so what I want to argue actually is that diverse training data, so more training data and better models and algorithms can actually improve the performance in practice. And what I mean with improved performance in practice is really it can improve out-of-distribution performance, which is what we are usually interested in practice. Okay, so let's see what I mean with out-of-distribution performance. So let's look at another experiment again. So here's a concrete experiment. So here we take the fast MRI data set, right? So this is collected at New York University again. And we split it into a training set and into the test set. That's just as before, right? But now we're also going to take another data set that also consists of knees, right? So it's not outrageous. It's also MRI images, also knees. But there are some slight differences on how this data set is obtained. For example, the frequency resolution is different, slice thickness, and so on. So the Berkeley MI people might know better the difference between those models, right? But there are some slight differences between the model. And I'm going to call this a Stanford test set as follows. And also the color code will be, in distribution will be blue for the following, and out of distribution will be orange. Okay? So now let's think about what might happen in terms of performance if we look at algorithms and we measure performance in terms on this in-distribution data set and on the out-of-distribution data set. So I want to look at different reconstruction methods. So there are, like, let's just say there are these three kinds of reconstruction methods. The first one is L1 minimization, or total variation minimization, right? So that's used classically for compressive sensing reconstruction. Like if you go to hospital today, most likely that will be used, right? Then there are neural networks, and technically L1 minimization is not trained, right? It's not trained on data, but there's this one regularization parameter, lambda, that is actually tuned based on the data, right? So you could say it's also trained in that sense. Make sense? Because that parameter we choose based on data. It's going to become important later. And then there are untrained neural networks. Those are neural networks that are not based on data. It's very similar to what Ben talked about yesterday, right? So those are neural networks that are only trained on the data that is given at test time. They also have some parameters, but very few, so let's say 5 parameters. And then there are these end-to-end networks, so the UNet, the variational network, and so on, and they have, like, let's say 50 million parameters, or whatever fit on your GPU, right? Like, that's roughly the size of those networks. Okay, and so now let's think through what we might expect. So what I'm plotting here is, so here we have the performance on the FastMRI dataset. So we look at the methods trained on FastMRI, right? So methods trained on FastMRI means for the neural network, it's trained on FastMRI data. For L1 minimization, it means the regularization parameters chosen based on FastMRI data, right? So that means methods trained on FastMRI. So here we evaluate on the FastMRI down there, and here we evaluate on the Stanford data. So now we can plot, or we can put a point for each method, right? So for example, if we have a point here, right, then it means the method gives 0.7 on FastMRI and gives 0.6 on the Stanford data. So what do you think? Where do the methods fall in this plot, roughly? What would you expect? What's your intuition? Yeah? Top left? Well, some methods are going to be more top left, right? So any thoughts on this?
No, but SSIM is like one is the best. Right?
One is the best, exactly. One is the best.
So it should be in the lower right.
No, lower right.
Lower right? Okay. Exactly. So, but the question is kind of like we wanna compare, let's say, L1 minimization to neural networks. So, for example, if you think that L1 minimization is going to suffer more under distribution shift, right? You would expect that. Or if you would expect the neural network to suffer more under distribution shift, you would expect it to be more below this line, right? And if you would expect your method to not be so sensitive to a distribution shift, you would expect it to be closer to the line, right? So then, like that is what I expected, at least something like that. That L1 minimization lies somewhat on the line, because I was thinking, okay, can't be that sensitive to the distribution because it's really just one parameter. The untrained networks, they perform a little bit better than L1 minimization, so a little bit higher, but also more or less on the line. And then I was expecting like UNet and variational network. So those are these neural networks. I was expecting them to be significantly below the line, and the intuition was that they are trained. There's 50 million parameters trained on the FastMRI data set, so I would expect them to be really tailored to this data set and so perform worse on this data set, right? Yeah, that's one possible outcome. Another possible outcome is like this, because it could be that the Stanford data is just harder than the New York University data. Maybe it's just more difficult needs or something like that, right? Who knows? Guess that doesn't make sense. But it could be that like they are scanners, right? They just have a worse signal-to-noise ratio, right? In this case, like the scores would be, then all scores would be dropping, right? So there are really two effects here. There should be something absolute, maybe, it's related to the difficulty of the data set, and then there should be something more related to relative comparisons of the methods, right? Okay, so here's what actually happens. So here is the data set shift, and here you see, like, so for each point is one method. So variational network, there are just different variations of the variational network. So there's like larger ones, smaller ones, things like that, right? And same for UNet, there are large units, small units, and so on. And even for A1 minimization, right? There's total variation minimization, there's wavelets as a sparsifying basis, and there's DCT as a sparsifying basis. And so what you can see here is that all methods perform significantly worse under the distribution shift, right? Because all methods are significantly below this line, right? But the important point is that the neural networks, they do not suffer more under those distribution shifts than L1 minimization and this untrained neural networks, right?
Yeah, but you could fix the L1 by moving
exactly.
the parameters.
You could fix that, and we're going to talk about that later. Good, very good point. But even if we fix the L1, let's say we fix the L1, move it up there, right? It's still going to be worse. But good point.
It is still.
It's still going to be much worse, right? But good point. Actually, so how we came about this experiment was, like, I'm really a fan of these untrained neural networks. I worked quite a lot on them. And my starting hypothesis was like, okay, maybe the untrained neural networks, if they stay here, but the variational networks, the neural networks all drop, then maybe finally they're going to be better, right? So that was like the thinking, but not true, as you see, right? Okay. So, and this really holds true for a number of distribution shifts, because now we talked about the data set shift. So now you could ask, yeah.
So have you done the experiment of just training a little bit on the target data?
Yeah, that helps significantly. Yeah, actually, just training a little bit. Good point. Because we need only very little data. And that's what we know from the scaling laws. So that helps significantly. Yeah. Okay, so this really holds true for other shifts as well. So here's adversarially filtered shifts. So that is a shift kind of like, those are, doesn't matter so much what it is. Those are like difficult to reconstruct images. And as you can see here, the same thing holds, like all the methods drop by a very similar amount under such a distribution shifts. Here you have another example, that's anatomy shift. That doesn't make that much sense, I guess, because you know whether you are scanning a brain or a knee, but like hypothetically, let's say you train on brains, right? And then you test on knees, there's significant drop, right? Doesn't perform very well. Okay. So now what we want to do is, like now we see that things perform significantly worse under distribution shift, right? So now what we would want to do is we would want to improve the performance under distribution shift. And here you have a few examples, like a UNet trained on brains, it really has like pretty bad artifacts or the variational network, right? So you can really see this in the images. It's not like it's not just a number, it's like a significant performance degradation. So what we would like to do is, we'd like to, move these things upwards. Moving these things upwards means improving performance under distribution shift.
Quick question, so are these supposed to be knees now in the reconstruction, but it's making brains, or?
So it's, so the experiment is, we train on brains, and then we
want to reconstruct knees, right?
Oh, sorry. So this is actually the other way around. So the plot is actually trained on brains, and this is SSIM on knees, but those are for trained on knees and then tested on brains. Sorry for that.
Okay.
Yeah.
Okay, good. So basically these circular things that you see
yes.
in the brains, they actually come from the knees.
They are actually also, they don't really, they're also in L1 minimization, right? It's just like that if you would, it's a relatively high undersampling factor. So if you would train on brains, it would just perform much better. Mm-hmm. Yeah, but good point.
So the artifacts are like some kind of aliasing?
They're aliasing from undersampling, but if you train your UNet and variational network on or actually on the brains, then it would be significantly better. Yeah. Okay, so now this is a very interesting paper here from some of our colleagues, so especially Ludwig Schmidt and Ben Recht. And what they did is they looked at exactly the same stuff for classification problems, also before us. And so what you can see here is the very similar plots, right? So methods, so all these points are different methods, and here is in distribution performance, and here is out of distribution performance, and what you can see is all the methods perform significantly worse under distribution shift for classification. So what's also very interesting in this plot is there are also robustness interventions, right? And there are also training with more data. So robustness intervention means there's a paper that says, we have this method, it helps under distribution shifts, right? So those are natural distribution shifts, and as you can see, the brown points, they are also on this line, roughly. So they are not really helping under distribution shifts, right? Because if they would be helping, the points should move up above this line. And what's also interesting is that some of these points, some of the green points are actually significantly above the line. So that kind of tells us that one thing that really seems to work under distribution shifts is to train on more data. But in this case, more data doesn't really mean like just more of the same. It typically means like more diverse data. It's hard to measure what that actually means, right? But that's kind of what happens here. Okay, but the takeaway from this really is that for classification problems, natural distribution shifts are an open research problem. So there's not really something that fixes that so that the method performs significantly better under distribution shift. Yeah.
But this more data observation is not a retraining using the new distribution.
It's not a retraining. Yeah. Good point. It's really just like, for example, let's say you have something like ImageNet, right? You could also just collect much more data from the internet, and you could train on that data. Yeah, and then you could hope that it performs better, and that's actually the case. Yeah. But turns out for prediction problems, very difficult problem. For image reconstruction problems, much easier problem, as you mentioned, so probably you were thinking about that. So for L1 minimization, it's actually really easy to improve the performance. So how do you do that? Well, like you can just take your data, right? You split it into Y, let's say, and you take a tiny part of the frequencies and you denote that as Y validation. So you just split it into a set of frequencies that you use to reconstruct and into a validation set, right? And then what you can do is you just train your method. So, like you reconstruct based on Y, right? And then you're just choosing the regularization parameter that minimizes the validation loss. So the loss computed on those frequencies. That gives you a reasonably good estimate how well you perform on how your reconstruction error is, right? And that allows to improve the performance for L1 minimization significantly, right? So under distribution shift for L1 minimization, as you pointed out, it's a relatively trivial problem to fix.
I think this has a name, right? Cross-validation.
Cross-validation, yeah.
But your goal here is to find a lambda that works for all the needs from this new scanner?
No, you do that for one given knee.
Yeah.
For one knee only.
Each knee.
Yeah, so you assume really that you put your knee in the scanner and then you want to do well. So you don't imagine that you're collecting a bunch of data at Stanford and then you're trying to find a method so you're really trying to do this example by example. Yeah. Okay, so now it turns out, well, but it doesn't help us that much, right? Because, now we know how to move those points up a little bit, but but it's still significantly worse than neural networks, but what we really want to do is we want to move those points upwards. So here it's not as clear as how to do that because we cannot do the same thing, right? Because we have a neural network that has 50 million parameters when we have like an MRI scan, much less than 50 million parameters. So we cannot just train the method on this data, right? But it turns out like a very similar idea actually works. And we call this test time training. So the idea is like during training, so this is how these methods are trained, right? So f of theta, that's our neural network. It's applied to the undersampled data or the noisy data. And this is the true image. So that's the supervised loss. So we can also define a self-supervised loss. So self-supervised loss is a loss that only depends on the noisy measurement, in this case, y, right? And so this is a self-supervised loss. So we train the method on the supervised loss and the self-supervised loss. And then at inference, we do the following. Like this is very much simplified, but just to illustrate roughly the idea. So we do test time training. So at inference, we again tune the parameters of the network on the measurement that we're given at inference. And of course, if we really just minimize that, we're going to overfit. So we also do some regularization and some tricks, but we do something very similar to this. And then we reconstruct based on with a neural network that we kind of fine-tuned on that one example that we are given at inference. And we call this test time training because at test time, like at inference, we are training again. So actually we call this test time training because there's a paper that they do test time training in classification. Unfortunately, it doesn't really work well for classification, but works very well. But this idea works very well for image reconstruction problems.
So your new training, is that fast?
It's not fast.
But is it? It's a retraining?
It's
or start.
Well, we call it test time training in the sense that you have your method that is trained, then you get a scan, let's say, and then you train your method a little bit, like shown here, and then you get a new model and you use it just for this example. Then you throw it away, right? And you start again, like for the next example, you start again with the model that you trained in the first place. Yeah.
Why do you throw away this sort of adapted kind of network? Because wouldn't it, like, if the more examples you get in, wouldn't you expect it sort of to learn more of the characteristics of what, I mean, assuming that it's the same scanner that you use?
Yeah, good point. I mean, in principle, it could work, but it really doesn't. And it's maybe related to, we saw this talk on catastrophic forgetting, right? Like from this talk, we also know, and from the results in catastrophic forgetting, that typically if you have a model and you train it on another task, it kind of forgets like the tasks from before. And I think right now we don't really have a method to do that well, but if we had a method to do that well, we would probably want to apply it here. Yeah.
We had a talk on how not to forget things maybe that could be implemented here.
Yeah. So that's exactly the talk. But I think that talk was really showing that you do often forget, if I understood correctly. Yeah.
But it also showed how you avoid it.
How you avoid it?
Yeah, but go in a certain direction.
Yeah, I mean, I also worked a little bit on this catastrophic forgetting, and my takeaway was really like this does not work well. Yeah. Unfortunately, and for this problem, I know for sure that it really does not work well, unfortunately. And it could be right that there's a method, yeah.
Is there a reason you use L1? Maybe I missed it.
Just by experimenting, the L1 worked much better, yeah. So what we typically do is, like, if we have as a supervised loss, we also typically use L1 or SSIM, typically get better performance than if we use L2.
The thing's differential with respect to that one norm, theta?
A differentiable aspect?
Well, you're minimizing over theta.
Yeah.
The L1 norms, I don't know about if you're going to use a gradient descent.
We use gradient descent, yeah.
That's what I was asking. It's differentiable respect to theta over the L1?
Yeah, it is. It gives. We have subgradients, right? So PyTorch gives us a subgradient, and then we use what PyTorch gives us, and that seems to work well. But it actually gives us a subgradient. Yeah.
Well,
for those.
That was a question I had from someone yesterday.
Yeah.
Like, well, how do you do subgradient descent? I know what a subgradient.
Yeah.
Yeah. I won't make you answer that question.
Yeah.
I think we should let you proceed.
Yeah.
Okay, so let's see how this works. So here is, so again, I have this coloring scheme, right? Like, so let's say we, let's look at the anatomy shifts again. So here, if we train on P and we test on Q, then on average, that is the performance we get. So train on P means, like, if we train on the brains, right, and test on the knees. So now if we train on the knees and we test on the knees, obviously we're going to perform much better, right? So that's where we really want. That's where we want to go, because obviously we cannot get better than, or with that model we cannot get better than that, right? Because we fixed the model. Okay, and this is the performance gap, and we call this the distribution shift performance gap because that's a gap that we have just because we're training on the wrong distribution for that problem. Okay, so now if we apply the test time training, then what happens is the following. So now if we train on Q and test on Q and we perform test time training, we actually get like a tiny performance improvement. And that is really expected because like think about a one minimization again. If you take a one minimization, you have like let's say 100 images and you use the same regularization parameter for 100 images, you get worse performance than you choose if you choose the right regularization parameter for each image individually, right? You get like a tiny improvement in terms of performance, and that's what we see here. And if we do train on P and test on Q and do test time training, then we don't get as good, right, as training on Q but testing on Q, but we get we close this performance gap significantly. So we call this the performance gap after test time training. And so that's what we're really interested in. And like by how much do we shrink this performance gap from this huge one to this hopefully smaller one? Okay. So in this example, it closes 99% of the performance gap. And so here are a few examples. So here's one distribution shift, like let's say anatomy shifts. There, the gap we close the gap by 99%. So for dataset shift, we close it by 87%, by modality shift by 96%, and for isolation shift by 97%. So it works a little bit differently depending on the distribution shift. And we also don't expect it to work for every distribution shift. But for the ones in MRI, it seems to be very effective. All right, so conclusions, yes?
So how long does it typically take to retrain your network? Is it like just 5 great iterations?
It's actually expensive, so it's good that you're asking that. So that's really like a weakness of the method is that it is slow, right? Because usually you have your neural network, you make one forward pass, you get your result, it's like super fast, right? That's really one of the big advantages of neural networks for those problems. So now you do test time training, now you do like 100 updates or 1,000 updates, 1,000 times more expensive, right? So much, much more expensive. So now it's as slow as one minimization again, right? So, yeah.
What if at the testing training, you only fine-tune some parameters, like the last layer? Would that provide similar benefits at test time, or it doesn't help?
I think it wouldn't accelerate things because, like, probably it wouldn't, because your network is still large, so computing the gradient even for a few parameters will still be expensive. But it could still work well, right? But I don't think it would really solve the computational issue. But there are some ideas potentially that helps, that might help with this computational issue. But right now we don't have a solution to this, unfortunately.
So
yeah.
Why didn't you do the L1 minimization?
Say again?
Why didn't you do L1 to L1 minimization?
He means L1 on the data term as well as the regularization term.
You mean in the... good
because
question.
you did that for the neural network,
right.
But you didn't do for the...
That's a good question. We might even have done that. I have to talk to Mohammed there. Yeah. Probably we did. Like, what does the BART toolbox use? Do they?
Fix?
Say again?
For which one? The fix L2.
It uses L2, okay, yeah. Yeah, but a good question. So maybe then L1 is going to move up a little bit on that line, right? Yeah, that.
What I expect.
Yeah. Okay, so conclusions are, so from the scaling law experiments, we predict, we don't know for sure, right? But we expect that there are only marginal in-distribution gains from scaling beyond a few thousand examples for image reconstruction problems. However, we expect that there are significant gains from building distributionally robust methods through either doing something like test time training, which is very slow, right? Or if you can do that, but we don't know really how to do that, through training on more diverse data. Because obviously if you Like let's say you have this distribution shift problem of brains and knees, right? If you train a method on both brains and knees, it's going to perform really well on brains and knees, and you don't have to do test time training, and you're going to be super fast, right? So that's what you really want to do, but it's kind of unclear how to, build such a data set. But in a way, the conclusion really is that for in-distribution data, for in-distribution performance, more data and better models really do not seem to help. But in reality, where you're really interested in distribution shifts, it seems like that better models, better algorithms like test time training, potentially other things, and also more data, but in this case, not just more of the same, but more diverse data really helps. And helps significantly, right? Because like those differences in making something distributionally robust, they are ways higher than the differences between like the worst and the best model, let's say, on FastMRI, right? Those are huge differences. And I also think more broadly that algorithms and better deep learning methods still have huge potential to further improve performance in practical imaging problems. And with practical imaging problems, I mean also things like, just to give one example, things like cardiac MRI or so, where things are moving, right? Like there are still a lot of gains to be expected by, also having better models and things like that. All right, so here are the references of the papers I talked about, and with that I would like to thank you very much for your attention.